Next speaker is Zilei Han from Tsinghua. Yeah, so the paper is solving string constraint with the regex dependent functions through transducers with priorities and variables. Zilei, if you are there, we don't see you. We don't see slides. So okay. We see slides, but we don't see you. We would like to see you too, if any. Okay, but if you have problems, you can go ahead without your face. We have a little face over the top right corner. Okay, now it disappeared. It's okay. It's okay. Go ahead. Go ahead. Yeah.
given marked by a pair of parentheses. The sub-expression included in it will be stored by the manager so that you can use the sub-expression matched by that later by using references like this. And simply, we have anchors. Anchors are just some special symbols that can match certain position of the input string without consuming any characters. Okay, so all three of these features are not present in the classical model of regular expressions. And just a quick example of how the semantics are standard. So let's consider in JavaScript, for example. If we consider the lazy variants of loop iterators, such as clean star here, according to the definition, it should match as few as possible. So we expect that to return the empty string. But actually, if you execute the code in JavaScript, like Node.js, it will return A instead of the empty string. It is because that this expression is included in another clean star. And in this context, the ACMA script standard as prohibits the mesh to be empty. Okay, so this actually shows that the behaviors of certain operators or expressions actually depends on the context. So it's context sensitive. We will get back to this later. And for now, let's introduce some formalism about what a real regular expression is. So here we use the BNF grammar. And as you can see, the regex we consider have some classical constructs such as union or concatenation. But we also add some new ones like capturing groups by a pair of parentheses, or the leading variants of plain star and plain plus, etc. As I have shown previously, that giving a denotational semantics is somewhat difficult. There have been some attempts in the literature by using like magic tree or lambda expression, but they are not adequate for like similar string constraints. So in this paper, we actually devised an automata model for it. So like we have given operational semantics to it. So this automata model, which we called prioritized string transducer, is abbreviated as PSSD. We can construct it for each regular expression E inductively as it is operational semantics. So what is PSSD? Here is its formal definition, but I will not go through it because it's very technical. But rather I will explain the intuition behind the design. Okay, so essentially PSSD is a finite state transducer or reading machine. So we can use like a graph representation here to illustrate it. And actually, we add two features to it. The first one is the priorities. So every non-deterministic transitions are ordered. So for example, if the control flow has reached a program has reached a state where there are multiple choices, we will take the transition that is with the highest priority. And more importantly, we introduce memory to this transducer model, which is a finite set of string variables. Each string variables can contain an unbounded string. So it's not hard to see why we introduce these two features. The memory are used to model the capturing groups, and the priorities are used to model the greedy and lazy dimension. And by the way, each transition of this model have an update function. So on each transition, the string variables will be updated. Okay, so here are some examples of how to construct the PSSD for the regular expression. Basically, it's a Thompson construction for the too special about this construction. But one thing that knows that may worth noting is that the accepting state is actually split into two sets. The first one of them is used to accept the empty world, while the other one is used to accept the non-empty world. So the reason for this distinction is rather technical, and you can read the paper, and I will not go through in this talk. And we actually have conducted some validation experiments to see if the semantics defined by our PSSC model is actually the same with the actual one in the programming languages. So we use JavaScript as the baseline and use Node.js as the implementation of the JavaScript language. And for each regular expression, we construct a PSSD and see if the output of it is actually equivalent to the output of its following code snippet. So we tested about 1,000 regexes, including all the operators defined in the syntax. And we have confirmed that the PSSD is consistent to the actual semantics of JavaScript. Okay, so maybe enough for the regular expression. And for now, let's talk about the theory and how to decide it. Okay, so our string theory, like others, will include some standard operators, such as identity, such as concatenation, regular constraints, or Boolean combination. But here we introduce some string manipulating functions, like extraction and replacement. So these two functions can take a regular expression as the parameters, and the regular expression are the regex, not the classical ones. And we have a theorem here that states that these two functions can actually be modeled by an equivalent PSSD. We introduce these two functions actually for the convenience of modeling real-world functions. As we have found in the experiments, most of the functions in the real-world scenarios can be modeled by these two functions. Okay, and later I will use the PSSD T to represent these two functions instead of using the literal form. Okay, so basically our theory is actually have two operators, like concatenation and the PSSD operator. So desirability, unfortunately and unsurprisingly, states that this theory is undecidable in general. It is unsurprisingly because it is strictly more expressive than a previous theory that is proposed and proved to be undecidable in 2016. So we cannot find some complete algorithm for this theory, but instead we propose some sequence calculus for solving these constraints. The sequence calculus is mostly standard by using some rules that is standard. But I think the most interesting rule here about our theory and the sequence calculus is backpropagation rules, which basically states that if you can compute the preimage of any regular constraints, like E here, under a function f, and if the preimage is actually regular and monadic decomposable, and we can actually backpropagate the regular constraints to the parameter of these functions. And what's nice about this rule is that if we can prove that x is not used anymore, we can actually eliminate x and reduce the number of string variables by one. So the most important part here is how to compute the preimage. It is actually shown in previous work that the preimage of concatenation is actually computable. So the only problem that remains here is the preimage of the PSSD computable. this is like the key theory of our work. That is the PSSD preserves regularity. So given a regular language and the PSST, we can actually compute the regular language that is the pre-image of this PSST. And we can construct the finite automaton representation in exponential time. So this conclusion may not be like straightforward as it says. Uh, since the PSSD is unbounded, it's actually an infinite state system. So by simulation, how can we like simulate an infinite state system by using a finite automaton? So there are some abstraction happening there, and these abstraction are actually very important for the construction of this range. But for technical reasons, I will not demonstrate it here. And if you're interested, you can see it in the full version of the paper, like in the appendix. And this regularity preserving property is very nice. So it can enables the decidability of a fragment of our theory. So this fragment it requires the straight line restriction, which is somewhat a canonical restriction of the string theory. So you can restrict the expressive power and maintains decidability. For those of you who are not familiar with string theory, straight line fragment actually requires that the formula is in its conjunctive normal form, and the conjuncts can be topologically sorted with respect to the dependency relation of these variables. So basically, if the variables in the formula does not have an interdependency, I mean the dependency graph is acyclic, the formula is straight line. So this straight line restriction is actually proposed to mimic the actual execution of sequential programs, which is represented in the static SQL assignment form. Okay, so for the straight line fragment, we can actually have a precision procedure for it. Let's see a quick example of how to do this. So for example, here's a straight line formula of it, and we can decide its satisfiability by iteratively computing the pre-image of it. So it's like, firstly, we can compute the pre-image concatenation. So it has been shown previously that it is computable, and it can be represented as a set of unions of Cartesian products of the regular language. So we can eliminate the string variable z here and choose non-deterministically a disjunct, and use the regular constraints to represent the whole assignment here. And secondly, of course, we can continue to eliminate the string variables y here. So we compute the pre-image of these regular constraints under the PSSD, and we got finally a constraint that is equivalent to the original one, but we only have a regular constraint in it. And of course, in this case, we only need to check the emptiness of these remaining constraints. And if the language is empty, is empty, the constraint is actually unsatisfiable, and vice versa. So that's a decision procedure for the straight line fragment. And for the last part, I'd like to talk a little bit about the implementation. We have a string solver that is called Ostrich. It has newly released a version that supports the theory and STR and some strings with real-world regular expressions. And of course, as far as we know, this is the first and the only solver with such support. And the implementation actually supports more features like anchors, but I have not introduced it in the form for Gravity. Okay, and for evaluation, we compare the ostrich with exposed in the V3, who better. So we can gain up to like 18 times speed up on some constraints. And their method is not guaranteed to have an answer, so it is complete incomplete. And for a straight line fragment, we have a complete sequence calculus for it. Okay, so a quick conclusion. In this work, we propose the first string theory and solver and support regex and regex dependent string functions. To precisely capture the semantics, we devised a new automata model called PSSD, and we proved a very important property of it, that is, it preserves regularity. And based on this conclusion, we proposed a sound sequence calculus for it, and it is actually complete for the straight line fragment. Okay, I think that's all for this talk. And let's see if there are any questions. Thank you.
Okay, thank you. Thank you. Are there questions from the audience? Yeah, wait. I come.
Thank you for the very nice talk. So the motivation for looking at these transducers was to model these, replace all and extract in real world regular expressions. My question is the expressiveness the same? So can you express all transducers with those real world regular expression operators?
Okay. No. Basically, the PSSD model is not the corresponding automata model for the real world regular expression. We can express every these regular expressions by a PSSD, but there are some PSSD that cannot be. I mean, the language of some PSSD is not expressible by regular expression. So PSSD is actually a very general automata model, which might be useful in other scenarios, not just when using like modeling these regular expressions.
Other questions from the audience?
Okay.
There are questions from online? I have a little question. What's the complexity of computing the inverse image in STR decidable fragment?
Okay. I think if there is no restriction on the PST, it should be tower hard. But if there is some restriction on PST, so for example, the PST is copyless, which states that on each update function, the string variable is only used once. The complexity can be reduced to double exponential.
Okay. Thank you.
Okay.
No other question. We thank the speaker again, and the session is over.